When counting mass quantities of almost anything, an efficient system that makes the task easier and less time-consuming can be very useful. Since chemical elements are usually found in incredibly large quantities, scientists have created a working system to help classify elements by mass. This system assigns every element its own average atomic mass and can be found on the periodic table. To help understand the way these numbers are found and used, I will use the analogy of balls. Imagine you are asked to count 1,000 tennis balls. The easiest way to do this would be to count by weight. This can be done by finding the average mass per ball and then weighing out the calculated mass. If all the balls are roughly the same mass, this can be achieved. We would start by taking a sample of, let's say, 10 balls. Just like any average, we can take the total mass of the 10 balls and divide by the number of balls sampled. Doing this gives us 57 grams per ball. Multiplying this by 1,000 will give us the total mass of 1,000 balls pretty accurately. This is the simple method of counting by weight, but when the situation gets more complicated, so do the calculations. Let's say there were two types of balls, each of which has its own average mass. In order to calculate the appropriate average mass, we need the average mass for each type and the relative abundance of each type. If these were the masses of 10 golf balls, and these were the masses of 10 tennis balls, the average for each type can easily be calculated as done previously. This will give us an average mass of 57 grams for the tennis balls and 45 grams for the golf balls. If we were to say for every 10 balls, 7 are golf balls and 3 are tennis balls, we can calculate percentages that represent each type's relative abundance. Golf balls are 70% abundant, and tennis balls are 30% abundant. By multiplying the abundance by its respective mass and adding them together, we can calculate the average mass for the entire population of balls. This comes out to 48.60 grams per ball. By multiplying this by 1,000, we can find what mass of balls we need to measure out to have a total of 1,000 balls. This is how scientists calculate the average atomic masses, which we find on the periodic table. Now let's relate our analogy to the real calculation. In nature, there are 3 different types of chlorine atoms: chlorine-35, chlorine-36, and chlorine-37. These are known as isotopes. Isotopes are atoms of the same element but with different number of neutrons. Neutral atoms have 17 protons and 17 electrons, but chlorine-35 has 18 neutrons, chlorine-36 has 19 neutrons, and chlorine-37 has 20 neutrons. Chlorine-35 has a mass of 34.9689 U. Chlorine-36 has a mass of 35.9683 U, and chlorine-37 has a mass of 36.9680 U. These are given masses of these atoms. They are not averages because all chlorine-35 atoms have the same mass. Looking at the natural abundance of each of these, we see that 75.76% of all chlorine in nature consists of chlorine-35, and 24.24% consists of chlorine-37. Chlorine-36 exists at such small amounts in nature that it is not considered in the calculation for average atomic mass. Using the information given about chlorine-35 and 37, try to calculate the average atomic mass of chlorine. Feel free to pause the video. By multiplying the mass of chlorine-35 by the relative abundance, you get chlorine-35's contribution to the average atomic mass. Adding the contribution of chlorine-37 to this will give us our final average atomic mass of chlorine in nature. We use this for calculations in chemistry all the time, so it is useful to know how it was found. Now let's solve for another average atomic mass. This time we'll be using carbon. All of the needed information is given. Please pause the video and give this problem a try. By using the same calculations as before, we can find the contributions of both carbon-12 and carbon-13. Once this is done, we simply add them together to find the average atomic mass of carbon. This is not that different from the mass of carbon-12, so does it really matter? Let's take a look. If we were to find the mass of 10,000 atoms using both of these numbers, we can see that there is 111 difference in them. This is just for 10,000 atoms. In reality, we would be dealing with many more. It is therefore important to use the contributions of carbon-13. Now for a moment, let's take a look at the units of average atomic mass. Unified atomic mass units are used as units for atomic mass. The common question is, what do these units stand for? To best understand this, the definition is necessary. Atomic mass units are defined as having 12 unified atomic mass units in one atom of carbon-12. You might have noticed in the calculation of average atomic mass that carbon-12 had a mass of 12.0000 unified atomic mass units, when actually it is equal to exactly 12. It can be considered to have an infinite number of significant figures. The value of one unified atomic mass unit is equal to 1/12 the mass of one atom of carbon-12. This also means that anything measured in unified atomic mass units is then proportional to the mass of carbon-12. For example, if there was an atom that was roughly twice as massive as an atom of carbon-12, it would be equal to roughly 24 unified atomic mass units.